and completed postdoctoral research at IIT Mumbai. He has authored 80 plus publications, including journal articles, conference papers, and book chapters. And he has edited 5 books on sustainable machining, additive manufacturing, bioimplants, sustainable materials, and biodegradable composites. Recognized internationally, he has been listed in Stanford University World's Top 2 Scientists during the period 2022 to 24. His research focuses on sustainable machining, additive manufacturing, surface engineering, tribology, coatings, green lubricants, and advanced food packaging technologies. A strong advocate of NEP 2020, he promotes multidisciplinary learning, innovation, and holistic development in higher education. So I welcome you, sir, to the evening session, the first session. And I request all of you, including the participants, to switch on your camera so that we can take a snap. I request all participants to switch on the camera so that we can take a snap.
Madam, please stop sharing the screen.
Okay, sorry.
Yes, all the participants, can you switch on your cameras, please?
Sir, have you taken?
Yes, ma'am.
Now I request Dr. Kishore sir to take over the session. Thank you.
Thank you so much. Just for the confirmation, madam, am I audible?
Yes, sir, you're audible.
Yes. Okay, just give me a moment.
Yes, sir.
Okay, thank you so much. I will share my screen and then we can start the session. Okay, can anyone confirm whether my screen is visible and am I clearly audible?
Yes, sir.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Thank you so much. Thank you so much. First of all, I would like to thank both Dr. Naidu as well as Dr. Pawni Madam for inviting me for this wonderful gathering of all the delegate members who have joined today. Today, we are going to discuss about design for additive manufacturing. So as this entire FDP is related nearby additive manufacturing, and I believe most of you are already expert in that particular domain, or some of you might be trying to come up with different ideas to work with additive manufacturing. Today, I am going to discuss about very important topic, design for additive manufacturing. We will also see how design for AM is entirely different than design for the conventional manufacturing process. So not only that, we will see the different things which we need to take care whenever we have to print a part. What are the things we have to consider specifically in the design phase? So when we go with the conventional manufacturing route, already we have a straightforward protocols. That protocols which has been developed by different standard agencies, including BIS, then we have ISO, we have ISI, then we have a ASME, ASTM, multiple different agencies already built up protocols. But when we deal with the additive manufacturing, even though the additive manufacturing is very prevalent in last 2 decades, but based on the protocols, still we are lagging. So we will see without the protocols also what kind of things we have to consider. And at last, probably in 8 to 10 slides, I will also show you the numerical values of quantification which are required based on which kind of process you are using and for what kind of component you have to design. So I would like to start now. First of all, when we say design for additive manufacturing, what does it mean? So it's a simple, very generic term which is used to describe certain rules and certain parameters for a part design. So let's say we want to produce a component. It can be any different component. Let me show you a component. I hope it might be visible to all of you through my camera. So it's a simple container. But if you will see this container, I will show you this side, top side. I am rotating this. First of all, we have a rotating component. It is, I believe, made up of one kind of polymer. For additive manufacturing, let's discuss and assume it's made up of PLA. So one thing is we have a rotating component. Apart from that, if you will see, we have a very big groove in this component. Plus, we have multiple different holes. I am just opening now. We have multiple different holes. So assume if we have to design this component, we have to take care of the holes, we have to take care of the groove, plus we have to take care of whether it is possible to make the holes and grooves exactly in this shape with additive manufacturing process itself. Whether these kind of sizes which I have shown you in this, probably 2 mm or 1 mm of the hole, are possible or not. If not, what can be done? If possible, how we can achieve this? Before we print it, so we have to consider multiple different things. Apart from that, particularly which equipment or instrument or method we are going to use to print this. As this is a PLA material, one of the basic choice should be FDM, fused deposition modeling. So apart from FDM also, we can use probably binder jetting to print exactly same component. But if you will use FDM or if you will use binder jetting, there is a high possibility a design consideration for both of the methods will differ, or we will have a different kind of design which we need to consider. Not only that, we also have to think about the design in X and Y axis and the design in Z axis. So most of the printer will have different scanning speed in X and Y axis and different speed in the build direction, which is usually the Z axis. So a lot of things we have to discuss, and one by one we will see with slowly we will discuss what kind of components, what kind of geometry, how we can print, what are the things to consider, what to keep in mind. So this is the overview of today's discussion for design for additive manufacturing. Now, the second specific definition of DfMA, it's not exactly a definition, it's just a takeover from the subject, is that it's a practice of designing products. Specifically, we have to keep in mind that we have to reduce the manufacturing and assembly difficulties and cost. So I am now showing you this component. It has two parts. If I will open this, you will see one part is this one, another part is this. So this, both of them need to assemble. Apart from that, in one of the component, we have a rotating part. So we need to print both of them separately, and then we have to assemble it together. So we have to design the entire component or assembly individually in such a way that after printing, it's easier for assembly. Not only that, if there are certain post-processing is required, that post-processing requirement should be as minimum as possible. Plus, we have to consider the economics behind all of the printing. So with this aim, we usually design a component. So whenever there is a complex geometry, we need to design in an entirely different way. And when we have very simple geometry, we usually do not bother that much about the design if it's a very common solid object. Now I would like to show you one specific object, and we will see how that object looks like when we design conventionally and how that object will look like when we design with the help of additive manufacturing. Let's start with an example. Now I would like to show you this small component. It's a cast iron hinge bracket. Usually in Airbus 320, to buckle the seat at top of the seat, you might have traveled by the air, most of you. So we have to open the buckle and then we have to attach it at the bottom so that we can fix the seat belt. For that, we need a component. This is the component. This is a steel bracket. So whenever we have to manufacture it conventionally, this component looks like this. So when we go with the conventional manufacturing process, there is a very simple way to manufacture it. We use the sheet metal, and with the sheet metal, we form this bottom part. Then we also use the casting. We form this part. Most of the time, we weld it or we bolt it with the help of any different joining process. Before that, we also go with the drilling operation at this part and this part. It's more or less very easy. But when we go with the additive manufacturing, you will see we have a similar looking object, but there are more complexity involved in this object. If you will see multiple places, we have support structures. These are usually support structures. Also, if you will see, apart from support structure, the overall material required to fabricate this component in case of additive manufacturing seems to be lesser than the conventional manufacturing. Now, the beauty of additive manufacturing is we can reduce the mass of the entire component. Not only we can reduce the mass of the entire component, we can still get the same function from the component. And in some cases, we will have a lot of benefits by reducing or making the component lighter. Now, with steel, this component is in the range of 155 gram, and with aluminum it's in the range of 120 gram. But when you make with the titanium with the help of additive manufacturing with SLS process, the component is somewhere in the range of 68 gram. So more than half of the weight is reduced, particularly by changing the manufacturing way of a component. Not only that, if it's a Airbus 320 and it has 240 seats, we have to use 240 plus component in that particular airplane. During the entire lifetime of the travel of that plane, the cost reduction, or sorry, the weight reduction of the component will save this much amount of fuel and 0.74 metric ton of CO2. So you just see, same component we can manufacture using the conventional route, same component we can manufacture using the additive manufacturing route. But because of the change in component and also its weight, we are able to see so much of benefit in terms of economic as well as in terms of environment. The only thing is, if you see this component, it looks a more challenging or more complex to design as compared to the left one. That's why it is important to understand how to design this kind of component. If you will see what they did, this is simply known as a classical problem of topology optimization. We are trying to optimize the topology of the same product by reducing the unnecessary material which is not required. So there is no function of this part of the material in the seat bracket. We only use the top side, and this additional part is provided because to support this structure, to increase the rigidity of this structure, to increase the life of this structure, these supports are required. Without that, it's very, very difficult to print it. And even if you will be able to print it, the strength is going to be very less. Not only that, apart from the topology optimization or certain kind of lattice structure, there are multiple different things we have to consider before designing a product, specifically in case of additive manufacturing. So this is the overall overview of what we have to think before designing the product in case of fabricating the product with additive manufacturing. So whenever for a conventional manufacturing individual who is going to manufacture the product with conventional manufacturing, designer has less work, but the production team has more work. But when we deal with the additive manufacturing, it's entirely other way around. Designer has to work more and production team has to work comparatively lesser in terms of overall producing the component. Now let's see what are the different design aspects and design consideration we have to take. So before designing the product, the entire design of additive manufacturing or design for additive manufacturing is divided into two categories. One category is known as design aspects. Another category is known as design consideration. So first category, design aspect, is something which can be quantified in design phase. So what are the examples of quantification in design phase? For example, we can quantify the thickness of the layer which is being printed with the help of any method in additive manufacturing. Let's say we are talking about FDM, and based on the focal point and based on our nozzle size, based on our heat source, we can say that we can print 2 mm thick layer every time. So we know the value. We are quantifying the thickness. Not only thickness, we can also quantify the angles. Let's say we have to print a 20-degree overhand product. That is also possible. We can also quantify the geometry, that the product should be 10 mm wide, 20 mm length, probably 7 mm in thickness. We can also quantify the orientation of the tool path, whether the layers are being deposited at 0 degree or 45 degree or 30 degree or 90 degree. So all things which we can quantify during the design phase, those things come under the category of design aspects. And there are certain things which we cannot quantify during or before the design phase, but they are critical when we discuss about the key performance indicator of the product. One of the very much important thing is surface roughness. So we have heard multiple times that in case of additive manufacturing component, surface finish is very poor, specifically when we deal with the FDM kind of printer or warm kind of printer. Surface roughness is very well, but surface roughness of a product we can only measure once the product is fabricated, and afterwards we can measure. So those will come under the category of design aspects and design consideration. And together, both of them, design aspects and design consideration, if you are taking care of both of these, we call it as a design for additive manufacturing. Now let's see what are the features which come under the category of design aspects and what are the features which are parameters which come under the category of design consideration. So everything we have to think in terms of parts. So whatever part we are fabricating, based on that, we have to think about design aspects as well as about the design consideration. For example, when we discuss about the design aspect, certain geometric features are quantifiable. Overhang structure are quantifiable. If we need a bore or a channel, so dimensions of the bore and channels are quantifiable. If we need a bridge kind of structure, that is beforehand we know in the product we need a bridge kind of structure, whether we need 1 bridge, 2 bridge, 3 bridge, what is going to be the dimension of the bridge, all those things are quantified. What is going to be the minimum wall thickness? What is going to be the minimum feature size? I have shown you this product. So I know if I want to fabricate this product and there is a hole of 2 mm or the smallest hole is equal to 2 mm. So I can say that the minimum feature size is 2 mm. Whether during fabrication this product needs a support or not, and if this product needs a support, the supports needs to be of which kind, from which inclination, what should be the dimensions, all of these things are quantifiable and come under the category of geometric features under design aspects. And there are certain process aspects which are quantifiable also come under the design aspect, like the layer thickness as well as the build orientation. Whether the layer thickness is 2 mm, 3 mm, 4 mm or 1 mm, or the orientation is 0 degree, 30 degree, 15 degree, 45 degree. So whenever it's quantifiable, we call it as the design aspects. When we get the information after fabricating the product, it can be accuracy, it can be roughness, it can be anisotropic nature, it can be the build time or cross section. We call it as a design consideration. Now let's discuss if we have to design an overhang feature, then what things we have to take care in the mind. Same slide I have put in the Word, so I'm going to skip it here. So let's see if we have to, starting with the geometric feature, there are multiple different geometric features. As I already mentioned,
Hello, sir.
Yes, madam. Maybe there is some technical issue. So, sir is left the meeting. Okay, just a minute, madam. I'm calling.
Hello, now am I audible, sir?
Yes, sir.
Yes, sir. Yes, sir. You're audible.
Thank you so much. Actually, there was lot of rain in this part of Chennai. That's why there was network issue.
Okay. Okay, sir. No issue.
Can
Okay, sir.
joining, can please anyone please tell me what was the last slide you have seen so that I can continue from that part.
What, sir?
Can anyone please tell me what was the last slide you have seen so that I can continue from that?
Yes, yes,
that
sir.
part?
Yes, sir. Yeah.
Yeah, now my slides are visible now.
Yes, sir.
Thank you. So I believe I was at the design aspects and design consideration.
Yes, sir. The same slide, sir. Yes.
Okay. Thank
Design
you.
considerations.
So let's start once again. So without delaying any further, I would like to show you. So when we discuss about the additive manufacturing, we categorize the design part in two ways. One thing is design aspect, another is design consideration. When we can quantify parameters which needs to taken care during the design part, those will come under the category of design aspects. Like we can quantify all the geometrical features of the product. For example, we can quantify how much overhang is required, whether it's 10 degree, 5 degree, 20 degree. What will be the dimension for the bores or the channels? What will be the length? What will be the depth? All those things we can quantify. What will be the thickness of the wall? We can quantify. In some cases, in most of the cases, we also quantify what is going to be the layer thickness. So whenever the things which are quantifiable and we can take care during the design phase, we can call it as a design aspect. But there are equally important things known as design consideration. Even though we cannot directly quantify those things, but we know there are certain things which are going to affect the key parameters like surface roughness. So if our thickness is very small, thickness means the layer thickness is small, we will have better surface roughness. If our thickness is more, we will have poor surface thickness. If our scanning speed is slow, we will have better surface roughness. If our scanning speed is high, we will have poor surface roughness. So even though we are not able to quantify directly, but during the design, we still know that there is a relationship between multiple parameters. So to get the product more accurate or to get a product with a better surface finish, we have to consider those parameters also during the design phase. Now let's see one by one about different kind of design phase I would like to show you, starting with the geometric features. Now, whenever we build a product with the help of conventional manufacturing, of course, we have to follow certain design laws based on the failure criteria and based on the geometries which we want to build. Similarly, with additive manufacturing, we have an entirely different set of design challenges. Again, depending on the type of machine which you are using, based on that, our layer thickness or the minimum or best resolution of the layer thickness is going to change. Not only that, the best resolution of the minimum feature size is going to change. Let's say if you want to print a hole, we are printing a product. In that product, we have a small hole as a feature. Whether that hole is 2 mm, 3 mm, 4 mm, what is the maximum possible hole size we can get and what is the minimum possible hole size we can get with the same printer. Based on that, we have to design our product. Also, in some cases, with some of the printer, it's very difficult to manufacture very big hole without the support. So whether we have to provide a support for printing the hole or not, that also we have to take care during the designing part. Now I am going to show you the design aspects of initial aspects, one of the aspect known as overhang. If you will see the slide, there are three different types of overhang. First overhang in this, you can see we have a vertical block, and from the top of that vertical block, we have a small horizontal block. So for the horizontal block, there is no support provided from the bottom. So during printing, we are printing on air, at least at the initial layers are printed at the air. So that last part is going to behave as a cantilever beam. Now, how much should be the length of cantilever we can build without support? It depends on multiple parameters. First of all, what kind of material we are using, what kind of printer we are using, what is the resolution of printer, what is the melting point of that particular material, what is the load bearing capacity of that material. Based on that, we have to decide whether we have to provide a support if the length is too high, or this length can be printed, and because of the cantilever shape, the product which is at the vertical side will be able to take care of the load. So those aspects we have to consider during the design phase. But if you will see the second part and the third part, which says angle overhang and the bridges, now how much angle we can easily print, whether it's a 20-degree angle or it's a 80-degree angle or it's a 90-degree angle. 90 degrees anyway, it's horizontal. So depending on the angle, whether we have to provide the support or we can print overhang structures without the support, those things we have to consider during the design. And if you will see the bridges, so there is a distance between two vertical components shown as D. Depending on the length of the D, if the length is very small as compared to the vertical component, we can easily support with the help of, because then the beam will act as a in this case the beam will be act as a simply supported beam. But if the D is too high, then we can expect an overhang, or we can say the buckling of the bridge. In that case, we need to provide a support. So these kind of important things we have to consider. Now, what are the solutions if we have challenges like this? If you will see the slide number 11, I am just zooming the slide. If you will see, depending on the size of the parallel shift, the D, we have to consider the limit. For example, with FDM, we can set a limit depending on the size of the vertical component, that we can print up to 7 mm of overhang without the support. If we need to print more than 7 mm for particle product, we definitely need a structure, support structure. So if you will see, or otherwise we have to change the design so that our product should not fail. So I am showing you another example of a added structure. Now we are coming at the slide number 12. Same vertical component along on top, it's a horizontal part. But if you will see, because the horizontal component overhang was too high, it is supported by a small, in the right side, if you can see, it is supported by a small triangular component. Even though the triangle component will be removed after the printing, but during the printing, as you cannot print directly on air, it is very much important to avoid the failure of the component to provide this kind of support. So whether to provide this support or to allow the printing with overhang is decided during the design phase. Now if you will see the next slide, there's a one specific example. In the left side, if you can see, there are multiple small vertical lines in that component. This is a topology optimized beam. In the topology optimized beam, just to print this, to avoid failure, they have provided multiple different support structures. And then during testing, they found out where is the possibility that this structure will fail. And then you can see the arrow marks. So during this arrow marks, once, because after printing, during the post-processing, before using this component, we will remove all the support structures. These support structures are only to provide load bearing and printable space with the additive manufacturing. So when this component is being used, from which area this component is failing, they have identified and then they have put the arrow marks. During the next phase of design, how they have changed it. If you will see the second part, this similar kind of structure, the load bearing is going to be higher. This, which I am zooming this area, if you will see this, the arrow is shown. Previously, this part was getting failed when the load was applied, but same part is redesigned, and now in the same part there are multiple different solid particles. If you will see, multiple different solid layers, and not only that, because of this the rigidity of the entire structure has increased. Similarly, if you will go with, I will go back to the top part, top arrow, which has been failed. So in the right side they have redesigned it, and during the redesigning again they have changed the entire type of design, and that new design, because of the additional support, is giving them more rigidity that will help to withstand the entire load of the capable. So this is one aspect of the design where we talk about the overhang. Similar to that, once the overhang has been designed, after designing, whether the component or whatever overhang limit you have set based on the printer. Let's say we have a printer, FDM printer, and we are printing the material PLA. Particularly in case of PLA, for horizontal block is give any dimension, maybe 20 centimeter. Based on that, we can print a vertical block of overhang up to 7 centimeter. If once we have designed that 7 centimeter, defined with the help of all the design aspects, whether that particular component is going to bear all the load or it will fail during the load, that we have to test, and whether the design needs change or the same design is passed. Depending on the size of the geometric features of the overhead, we will check the aspect. If it's passed, we will directly proceed. If not, again we will provide a possible alternative design, and this loop will go on till we have to decide whether support structure is needed, or we can directly go with the overhang and then we can proceed. So this was about our normal overhang structures. In some cases, we also have a angled overhang. So we have initially seen 3 different kind of overhang. The second one was the angle overhang. So when we go with the printing, particularly with the angled overhang, plus 45 and minus 45 degree overhang are comparatively easily possible in most of the extrusion based additive manufacturing tech. Even in powder bed fusion additive tech, support structures, specifically even with a steeper angle, are also possible. But if we have to move beyond plus 45 and minus 45, then the situation become more tricky. So I will show you the next slide. If you will see now the slide number 16, I am zooming that part. So to print this part, we have multiple different overhang, 40 degree, 45 degree, 50 degree, 55 degree till 70 degree. So as the angle is getting increased, and you have to see the back side of the overhang, what happened to print the overhang, the material need a support from the back side of powder in case of SLS technique. Whenever we go with selective laser sintering or selective laser melting, the backside powder will provide support to the top side where you are giving the laser source and it is getting heated. That backside powder will also partially melt and attach with the overhang. When your overhang is beyond plus 45, then the deformation or remelting or half melting of the powders is going to be higher. In that case, you will have very bad surface roughness. So we have to find out the limit based on the printer. As I said, for SLM, still it's possible to print up to 70 degrees Celsius. But if we are going with the FDM, plus 45 to minus 45 are possible without the support structure. Beyond that, we have to go with the support structure. Now let's discuss about the next design features, which is known as bridge or bridging. I'm going to show you this figure. You will see this figure. Again, we have a solid horizontal block. On top of a horizontal block, at the both side, we have a vertical block. Both vertical block are connected with a horizontal block. Now that horizontal block is only supported at the end. It is not entirely supported from the center part. So because it is not supported at the center part, we need to make sure that how much of the length which is marked by the red color, is possible to print on air or whose load can be bared by those vertical block. Now, again, this also depends not only on the material, it also depends on the kind of machine you are using and kind of method you are using. So depending on that, as a designer for additive manufacturing, we have to find out the constraints. Based on that, we can say yes, up to 10 mm is possible. Beyond 10 mm, we have to provide the support structure. Otherwise, this is not possible, particularly in this geometry. Otherwise, another way is to entirely rotate the printable structure. Instead of printing the horizontal block, we rotate the entire design by 90°, then we can easily print this structure. But as soon as you will rotate the block, what will happen? The printing time will change. Why printing will change? Because the resolution and the scanning speed in Y direction in most of the machines are slower as compared to the X and Y direction. So this is a very tricky thing, whether we have to provide a support structure and you need to go for the post processing and then you need to again cut down, that is more economical or that will take more time, or just changing the orientation of the build will take less time and less money. Decide, you as a designer, we have to decide on both things. Depending on the time requirement, product quality, as well as the final outcome, we have to decide whether we can print horizontally or we can rotate it and print vertically or provide a support structure. So those kind of decisions need to be taken care by the designer. Now let's see the next challenge of geometrical features known as pores and channels. So I would like to tell you, whenever there is a channel or whenever there is a hollow shape in any kind of product, the load bearing capacity is going to get reduced. Not only that, because you are printing in vertical direction, once you have printed it in vertical direction, before you print the next layer, if there is a hollow part at the bottom, the top part will start moving down before solidifying itself. That will deform the structure. So that's a quite challenging task to make a bore or channels in case of additive manufacturing if the material or the component is not designed properly. Now, what are the possible solutions for that? So I'm going to show you this particular figure. The channel need to be built. The shape of the channel was expected to be a circular. Because circle has a curve, it's always more challenging to make a perfect circle with additive manufacturing because of the limitation of the tool path or because of the limitation of the layer thickness. So instead of a exact circle, if diamond kind of shape or teardrop shape, the center part which you can see is teardrop and the last part is a diamond shape. If same kind of work is possible with this kind of shape, then with additive manufacturing it's easier to print the teardrop shape as well as the diamond shape because they provide more support to the entire product as compared to the circular one. And if it's not at all possible to use circular one, then it is always suggested that you make a smaller dimension circle or channel, and later in the post processing you can do the boring operation and make the channel. So whether to go for the post processing or to just change the shape of the printable part, depending on its application and depending on the limitations, as a designer we have to decide. This is about the boring and the channels. The next aspect is, you can see, is the hollow structure. I am going to show you the left side if you see. Now this is a product. This product is a U-shaped product. At horizontal we have a one block, then from the last extreme left we have a vertical block, and again from the top we have a horizontal block, but in between we have hole. Now if we have to print like this, definitely we have to provide the support material in between if the overhang or the bridge size is too much. So the solution for this is, if you don't want to waste the material, you want to save the material in the design shape, instead of printing in this direction, you can just change the build direction. You can see the right side. Entire same product, you can just change the orientation. By changing the orientation, now we can make a hole in vertical axis. But while you are using the product, you can realign in the horizontal axis. But by doing this, what you have achieved, you have simply saved lot of material which was used for the supporting the overhang. Apart from that, not only you have saved the material, you also save the post processing time. During that post processing, you have to cut down the internal material. So these are the design aspects we have to think very critically. Now let's see the next part, which are known as lateral hole. During the design strategies, we have to find out what is the minimum possible size of hole can be printed with the printer which you are using. Not only that, what is the maximum size of hole we can print. If you will see this, in the lateral hole, first image shown a very crisp less than 10 mm diameter hole which can be printed very easily, not a problem. But as soon as the size of the hole increases, then because the size is increasing, the number of layer which need to be print will increase multiple times. The deformation due to higher temperature and due to lack of support will increase multiple times. So what will happen, even though if you want to print a circular hole, you will end up with an uh, elliptical hole where the major axis and minor axis dimensions are going to be different because of the deformation. And just to avoid that, we have to make sure that we have to provide the support structure if the size of the hole is huge. Or if you are not willing to provide the support structure, then we have to find out whether same kind of work or application we can just change the shape of the hole instead of the entire circular hole. If we can do with the teardrop hole, in this you can see, particularly by making the hole shape teardrop or diamond, we can minimize the overhang area. If we minimize the overhang area, we will have better support for the hole. So as a designer, all these things we have to consider. Whether what is the size of the hole, what is the shape of the hole, support structure is required, if the same applications can be done with different type of hole, how much time should be required, what should be the build orientation, all those things we have to consider under the design aspect. Now moving to the next part, this is also related to the vertical holes in FDM. I am showing you this slide. If you see the last part, right side, so with the slicer, when you are working with the software, our aim was to make a hole which looks like the top part. The slicer diameter is shown here. But once the hole is printed, because of the deformation in multiple layers, as well as because of the increase in load on the lower layers, instead of having a perfect diameter, you will end up with the elliptical type, which is shown in second part and the third part. So actual diameter will be slightly different, and post compression, again extruded layer will be slightly different, which is not accepted. So when you have bigger size of hole and you cannot change the shape of the hole, then there are only two options: either to provide the support structure, and if you believe support structure is going to be more time taking or more costly to remove, we can simply reduce the size of the hole during printing, and after printing we can again enlarge the hole by drilling method. So these kind of decision we have to take whenever we design for additive manufacturing. Now let's move ahead. Apart from holes, another feature which we discuss during the printing is known as wall thickness. Now, how much wall thickness, minimum wall thickness which we can print, it depends on the resolution of your material, resolution of your component. Apart from the resolution, it also depends on the focal length of the laser, if it's a laser source, or if you are going with the FDM, then what is the size of the wire which you are using, or what is the melting temperature or the nozzle orifice. So depending on multiple things, minimum wall thickness is decided. So I will show you once again. If you see, the left image and the right image, if you, even though the minimum wall thickness is assumed to be 1 mm, and if you want to print this block of 20 by 20 with 1 mm thickness, it's highly unlikely that because of this 1 mm, the entire product will be able to withstand the load. So, lot of stress analysis needs to be done before printing the product, and it is recommended to have minimum wall thickness, particularly in the case of 20 to 20 block, is 3 mm. So this 3 mm is not randomly, which I have just now calculated. It is based on the stresses developed on the entire structure during printing as well as the after printing. During printing, there will be a lot of residual stresses and lot of deformation. But after printing also, whenever we are going to use this particular component, there will be some residual stresses stored in it, plus weight of the entire component is acting always even after printing. Now, there are certain kind of geometrical features which seems quite difficult to print, but if you will simply divide those features in two parts and then later you can assemble it, that's also possible. So that is known as splitting up your model. So if you will see I will show you this image. If we want to print a sphere of 20 centimeter diameter, we need to provide lot of support from the backside in the vertical direction to maintain the circularity of the sphere. Now, what is the possible solution for this if you do not want to use the support? Now, I will show you the solution. Instead of using the support, you can simply print two half semi-spheres. At the again from the center, you will always have the support because it's the biggest dimension, that is the diameter at the center. So you can print two different half hemisphere and later you can assemble it together. So that is also possible. In some cases, these kind of solutions are readily available. In some cases, we have to think out of the box to get to the solution whenever we design for the additive manufacturing. Now moving ahead, there are certain components which need different kind of solutions. Now I will show you one of the example. This is an example of adding hardware or inserts. So if you will see this image, there they are printing a turbine. Now that turbine is usually subjected to very high temperature. To cool that turbine, we need to provide a material which has very high thermal conductivity, which can dissipate good amount of heat in less amount of time. So during the printing itself, what they did, they have printed the half part of the wheel, and on top of it, I will just zoom it, you can see they have kept the copper inserts. Now the good thing about the copper is it has very high thermal conductivity. So whenever during the usage, there will going to be higher temperature is being developed. Because copper has higher thermal conductivity, copper can dissipate the heat faster as compared to the normal steel. So they have kept it at the center, and again on top of it, they have started printing. So in this particular blade, already there is a copper inserts, but these things we can only do if you have designed for the placing of the copper insert at the half part, and later you have given it a break, and then somebody has put an insert, and again we have started the printing once again. So this is another part of design aspects, we can say. Now there is a very challenging thing is to print the threads. Lot of component, because of the assembly we need to provide the threads, but if you are printing a component made up of PLA and if you are also making the threads made up of PLA, then what will happen? Only because of the thread, the life of the component is going to get reduced, because we know PLA is a polymer, and if you will apply load and you will insert the steel screw in that PLA component, then because of screwing and unscrewing multiple times, the threads in the PLA will worn out. So to provide a solution, what they did, they have printed the entire component with the help of PLA, but only wherever the threads are required. If you will see, I will just show you. Only wherever the threads are required, they have provided the threaded steel parts. So just by changing this small thing, wherever you have to do the assembly, they have increased the life of the entire printer or entire product. So these kind of aspects I am talking about. So design aspects are very much important when we have to take care of each and everything depending on the type of product we are printing. Now moving to the last two parts of the design aspects. One is known as process parameter, another is known as layer thickness. Now the process parameter is one thing which we have to crucially select before going for the printing, depending on what is the priority. You can select very fast processing parameter, that means scanning speed is fast, higher layer thickness should be higher if you want to save time which is required for printing the product. If time is the priority, you can go in that way. But if surface roughness you want really good, or dimensional accuracy you want really good, or you want a better tolerances, then you have to use the different set of process parameters. Layer thickness is also very important whenever we deal with the quality of the print. If you have very small layer thickness, it's going to give you better quality of surface roughness. If your layer thickness is high, it will save the time, but the surface thickness and the tolerances are going to be sacrificed. Plus your dimensional accuracy is also going to get sacrificed. There are certain products where you can combine these two. I will show you an example. Let's move ahead. If you will see this example. So if you have to make an arc like this and you want a perfect arc, and if your layer thickness is big, then you will not be able to get the perfect arc. You will be ending up with the horizontal blocks. But what you can do, you can use the adaptive slicing. Adaptive slicing means the features where curvature is not there, you can use higher layer thickness, and the features where we have a curvature, particularly for those part, we can go with the smaller layer thickness. So you can see this B part. At the bottom side, the layer thickness is high, but as soon as the arc or the curvature comes, the size of the layer thickness reduces. So with this, what you can do, you can get a better curvature. Not only that, you will get a better surface finish. The only trade-off is you need more time. So as a designer, depending on the product, depending on the capability of the equipment, depending on the method which you are using, we have to select either to go for this side or to go for that side, or we have to decide. Now moving ahead, one of the most important discussion regarding the design aspect is the build orientation. So there are multiple different products which you can build with different kind of orientation. Just now I have given you an example of a sphere. I can build a sphere with the help of supports at 0-degree orientation, or I can also build the sphere again with the supports at 90-degree orientation. I can also build the sphere with supports with 45-degree of orientation. Now in all three cases, if my build is 0-degree, I will save a lot of time for sure, because in X and Y direction, the speed is always higher as compared to the Z direction. But if I will build vertically, then I will get a different kind of properties in that sphere. So whether I need a sphere which can withstand more tensile load, or I need a sphere which can withstand more compressive load, or I need a sphere which can withstand more shear load. Depending on the type of the load, we can decide the built orientation. So there are few examples. If you will see here a 3D model, so the curvature is given. You can build this curvature keeping at the horizontal direction, or you can build the entirely same thing keeping at the vertical direction. Not only that, if you will see the next component, horizontally also you can build like this, and also you can build this at 45 degree. There are two things to consider. Whenever you will build at 45 degree or a different orientation, you have to provide more support. So more amount of material will be wastage. But whether that more amount of wastage of material can be compensated by better properties which are required by the product for any specific application, those kind of questions designer have to give. Now I will move forward slightly faster because I have already wasted some time during the internet connectivity. So what are the main effects of the built orientation? Let's say we have built a product which is 0 degree in orientation or which is 90 degree in orientation. If you will see this particular figure, if we have built layer by layer in 0 degree orientation and then we are applying the tensile load, then what will happen when we are applying the tensile load? The product is going to fail prematurely because the joints will fail faster. But exactly same product, if you will apply a bending load, 3-point bending load, the product will be behaving as a very strong component. Now exactly this 3-point bending load, if you are applying when the product is built by a vertical orientation or 90 degree orientation, you can see back. Now in this case, the part will be weak because wherever you have the joint between the multiple layers, and at that joint if you are applying the load, because of the failure in the joint, your product will fail. That's why I am saying depending on the type of applications for which you want to use this kind of product, for that kind of application, we have to first think which kind of load will come, whether it will be a tensile load or it's a compressive load, it's a shear load. Depending on that also we have to decide what kind of geometry or what kind of built orientation we have to choose. That's also a very important product. Now we have completed all the design aspects of additive manufacturing. So initially, if you will remember, we have divided the entire part into design aspects and the design consideration. Now we will see, so till now whatever we have discussed, all those things are quantifiable during the design phase itself. Now we are discussing about the design consideration which are not quantifiable during the design phase, but there are a lot of parameters which are going to affect the final product in case of if we have not considered them. Now let's just see what are those effects. Initially, starting with one of the most important thing is anisotropic nature. Additive manufacturing is not isotropic, means it is not able to make a component which is isotropic. First of all, we have to understand what is the difference between the isotropic and anisotropic component. Isotropic is something which will show you almost similar kind of property in all the directions. If you are applying a tensile load, or you are applying a compressive load, or you are applying a shearing load, almost, or you can say, sorry, not exactly the load, it will show you similar properties in all direction. That is the right word. Isotropic is something which will show you similar properties in all the direction. And isotropic are those kind of components or materials which will show you different properties in different directions. So additive manufacturing will fabricate a component which will always be anisotropic in nature. So in different direction you will have a different properties. So I will show you 4 different examples. So if you are using a laminate sheet metal method to fabricate the component, because of the laminar nature, means there will be multiple different layers of the sheet. In vertical direction, your properties will be different. In the horizontal direction, you will have lesser strength because of its laminar nature. That will make the component anisotropic. if our build direction is 45 degree in one layer and again minus 45 degree in second layer, so in every layer we will have different properties. This is possible in case of FDM kind of printer. Now if you will see the third kind of printer, which is usually which has multiple different fibers in the matrix itself, whenever we are printing the composite. Now depending on the alignment of the short fibers which you have filled inside the resins during printing the composites, properties are going to change in different direction, because alignment will be in one direction or in the other direction. So depending on the direction of the fibers, properties are going to change. So these are anisotropic in nature. And additive manufacturing is also very well known for printing different kind of lattice structures. So those lattice structures can be auxetic in nature or it can be normal lattice structure. In both cases, depending on the type of lattice, the properties in different direction is going to be. That's why we have to think about the applications and we have to understand particularly what is the requirement of the product which we are printing. Based on the requirement of the printing, we have to take a call whether we have to print which kind of lattice structure, or we have to print what kind of build orientation, or we have to print which kind of thickness. So this is about the anisotropic behavior of the material. Now I will show you one more design consideration aspect which is closely related to anisotropy. Let's say if you want to print this kind of metallic component, and we have an option either to print in the horizontal direction at 0 degree build orientation, or we have an option to build in the vertical direction at 90 degree print direction. So you will see this particular component, because it is being printed with 0 degree build direction, particularly near to the joining at the leg, it will be slightly weaker. Why it will be slightly weaker? Because at the center there is a gap. Again, then there is a more load is being transferred in both the legs. If you will print the entire same product in the vertical direction, I will show you in the vertical direction, the last corner part you will can see will be slightly weaker. Because the geometry is continuously changing from top to bottom with slight change in build orientation, load bearing capacity at different part of the same component is going to be different, and that also depends on the build direction. So if there are certain places which are very much example, which is very much important, if you know what kind, for which kind of applications you are going to use this component, you can decide whether to print in 0 degree build orientation, or you can print with the 90 degree build orientation. About some of the examples also suggest I am going to show you. You can print the bottom part with plus 45 and the top part with minus 45 to increase the overall load bearing capacity, not only in the horizontal direction from one side, also in the vertical direction the other side. So the bottom part component is built with different build orientation, top part of the component is built in different build orientation, and later you can assemble this component so that both the weakness of this component can be sorted out instead of printing with only with 0 degree and 90 degree. So these kind of questions, as a designer for additive manufacturing, we have to consider. Now I believe I have limited time and you have one more lecture, so probably I am going to rush through a couple of slides and then we can go with the question answers. Now depending on the layer surface, depending on the thickness of the layer which you are allowed to print, minimum thickness or maximum thickness, your surface roughness of the component will change. So layer, because additive manufacturing is layer by layer printing, you will have, if you have to print a component of 40 centimeter and each layer is 2 centimeter each, that means you are at least going to print 20 layers, and depending on the shape of the curvature of the 20 layers, you will have different peaks and valleys at the corners, and the surface roughness is going to be entirely changed. Instead of 2 mm, if you are changing the thickness of layer as 4 mm, you only need to print 10 layers instead of 20 layers, but you will print 10 layers which will have bigger peaks and valleys. Surface roughness is again going to get changed. So surface roughness will depend on not only on the layers size, apart from the layer size, what is the scanning speed, what is the resolution of the printer, what kind of material you are using, everything will dictate surface roughness. And not only that, the surface, the thickness layer also dictate the build time, whether the component is being built in 10 minutes or it is being built in 20 minutes. It depends what kind of parameter you are using, what is the slicing strategy you have used, whether all the thickness, all the layer thickness are same, or big you have chosen bigger layer thickness or you have chosen a smaller layer thickness. Those things are very much important to consider. Apart from that, we have to discuss about cross-sectional area of the parts. Again, I am going to show you an example. So, in certain cases, there are some products which are built on a base, and that base will become the part of the product. Specifically, whenever we are dealing with a metal printing, so there will be a base, and on top of that base we usually print a product. So there are two options: either we have to cut down the product with the help of wire ADM and remove the base, or in some cases that base will also become the part of the product. Now, good number of times the product failure happens when there is mismatch between the base property and the printed part property. And why there is a mismatch? Because either there was no preheating done in the base, and usually whenever, as soon as you will print the first layer of the material, there will be a tremendous amount of heat that will be generated, and that heat will start passing through base itself. That will affect the adhesion between different layers of the material, and also adhesion between the part as well as the base. So for that, we have to understand that it's very much important to preheat the base before starting the printing. So this was all about the design aspects and design considerations whenever we discuss about the design for additive manufacturing. So we have to take, before designing the product, we have to take care of lot of things. In case of conventional manufacturing, designer have a limited scope, but in case of additive manufacturing, designer have lot of things to do as compared to the manufacturer. Now I am just scrolling some of the values. If you will see this, if you want to print supported wall with two different walls, then we have a different thickness for different kind of methods. If we are going with FDM, 0.8 mm is possible, minimum thickness. If we are going with SLA, 0.5 is possible. But if we are going with binder jetting, minimum is 2 mm is possible, even with the best of the best printers. So that's why I'm saying it's not only about the geometry, it's also about the method which we are going to use it. So I have a lot of slides similar to that, which shows the data. Whenever you are designing something, what is the minimum feature, what is the maximum feature, what is the pin diameter possible, what are the tolerance possible based on the entire product. So all of this information is provided in one of the book published by our group known as Hybrid Metal Additive Manufacturing. Now the session is open for question and answer. Please feel free to have a discussion about the design for additive manufacturing. And I believe I have taken so much of time in between. So some quick questions, and then second resource person will start the session. Any questions from anyone? Any questions regarding the DfMA? Any aspects related to overhang, build orientation, layer thickness, design aspects, design consideration, anisotropy? Anyone? Okay.
Okay, thank you, sir.
Thank you so much, Naidu sir. And again, sorry for the interruption in between, but thank you for the invitation.